Victor III submarine K-488 breaks the surface off Kamchatka in February 1981. Ice-cold spray hammers the sail as the deck officer climbs topside. He scans the bow section and counts 14 bare steel patches where rubber tiles should be. Each missing tile is a meter square, 22 kilograms of synthetic rubber that absorbed active sonar pulses during the patrol. Now those patches reflect sonar like polished mirrors. The boat was supposed to slip through NATO listening posts undetected. Instead, every bare spot broadcast its position across the North Pacific. The officer radios the count to the captain below. 14 tiles gone. The submarine's stealth advantage has peeled away at depth, and no one yet knows why the adhesive failed. Shipyard crews swarm K-488 the moment the boat docks at Petropavlovsk. Inspectors move down the hull with handheld calipers, measuring each gap where tiles have detached. They record dimensions, photograph the exposed steel, and scrape adhesive residue into sample jars. The bare sections will bounce back active sonar at full strength, negating the coating's acoustic advantage. Western attack submarines hunting with 14 kHz pulses will see K-488 as clearly as any uncoated Victor-class boat. The chief engineer pulls the patrol log and cross-references dive profiles with temperature readings. No collision, no combat maneuver, just routine operations. The chief engineer reviews the patrol log in the base office. On day 12, K-488 dove to 240 meters during a NATO surveillance evasion. Surface water temperature that morning was 18 degrees Celsius. At depth, the hull steel cooled to 4 degrees. The temperature drop stressed the adhesive bond between rubber and steel. Hydrostatic pressure at 240 meters compressed the tile's outer surface, while the inner bonding layer contracted with the chilling hull. That mismatch created shear forces the adhesive could not survive. The engineer marks the dive profile with a red pen. Thermal cycling and pressure differential. The tiles were doomed the moment the boat went deep in cold water. Maintenance crews prepare the replacement tile requisition. Each tile is 1 meter square, 22 kilograms of synthetic rubber with embedded voids for acoustic absorption. The tiles must be hand-glued to the hull's curved surface, then riveted every 30 centimeters as backup attachment. The work requires dry dock, scaffolding access to the entire forward section, and 3 weeks of round-the-clock shifts. K-488 will sit pierside while newer boats take patrol slots. The chief signs the order and sends it to the supply depot in Vladivostok. He knows the tiles will arrive, the crew will install them, and the next patrol will likely shed another dozen. The cycle repeats. Leningrad, 1963. The TSNII-45 Materials Laboratory receives a wooden crate from the Moscow Naval Archive. Inside, a rubber tile recovered from German U-boat U-1105, scuttled in 1945 off the Danish coast. The sample spent 18 years in a warehouse, exposed to temperature swings and humidity. The lead engineer lifts the tile with both hands. The rubber surface, once elastic, has hardened and lost flexibility. He clamps one edge in a tensile tester and pulls. The material cracks and crumbles at only 60% of its original rated strength. The Nazi Alberic coating was the best sonar countermeasure of the war. Now the Soviets hold the degraded fragment with no manufacturing instructions. The TSNII-45 team runs spectroscopic analysis on the crumbled rubber. The base polymer is polyisobutylene, a synthetic rubber sold under the German trade name Opinol before the war. But the cross-linking agents and plasticizers that gave Alberic its acoustic properties have volatilized over 2 decades. The infrared spectrum shows only degradation byproducts. The engineers search captured German records. Allied bombing destroyed the IG Farben chemical plants in 1944 and 1945, and most manufacturing documentation burned with them. No complete Alberic formula survived the war. The Soviets have a target performance and a list of missing ingredients, nothing more. The lab attempts a first synthesis using available Soviet polymers. They cast a prototype tile with a polyisobutylene matrix, embed air voids for acoustic absorption, and bond it to a steel test plate. The tile goes into a seawater immersion tank at 18 degrees Celsius. After 6 weeks, the rubber surface has begun to dissolve. polymer chains are breaking down in the salt water, and the material has lost structural integrity. The engineers pull the tile out and test its acoustic absorption. It fails to match the original German performance profile. Incoming sonar pulses pass through the degraded rubber and reflect off the steel backing at 70% strength, instead of the target 15%. Moscow issues a directive in early 1964. The Victor-class submarine program requires an operational anechoic coating by 1967. NATO attack submarines are getting quieter, and Soviet boats must reduce their acoustic signatures to maintain deterrence. The TSN-II-45 engineers now have 3 years to reverse engineer a polymer system from fragmentary chemical data and acoustic performance targets. They have no German manufacturing specifications, no complete formula, and no time for methodical trial and error. The lead engineer briefs his team in the Leningrad lab. They will test every polymer combination available in the Soviet chemical inventory until one survives seawater immersion and matches the absorption profile. TSN-II-45, 1976. The lab successfully bonds a new rubber formulation to a steel test plate. The prototype tile goes into the pressure chamber. Engineers cycle the pressure to simulate 300 meters depth, then run 500 thermal cycles from 18 degrees down to 4 degrees and back. The adhesive bond holds. No delamination, no cracking. The polymer survives seawater immersion for 12 weeks with less than 5% degradation. Acoustic testing shows absorption performance matching the original German Alberic profile. 85% of incident sonar energy converted to heat, only 15% reflected. The ministry approves production. Victor 3 submarines will carry the first operational Soviet anechoic coating. Victor III submarine K-367 departs Severomorsk in September 1978. The hull is covered with 4,200 individual tiles, 85% of the boat's surface area. Each tile is glued and riveted according to TSNII-45 specifications. The coating represents a decade of materials research and the ministry's confidence that Soviet submarines can now match Western stealth. K-367's mission: patrol the GI-UK gap between Greenland, Iceland, and the United Kingdom, the choke point where NATO tracks every Soviet boat leaving the Barents Sea. The captain orders slow speed and minimal cavitation. The anechoic coating should cut the boat's acoustic signature in half. NATO listening posts should hear nothing. Day 14 of the patrol. K-367 is transiting north of the Faroe Islands when NATO surveillance aircraft appear overhead. The captain orders an emergency dive to 220 meters to evade detection. The boat descends through the thermocline. 90 seconds into the dive, the sonar operator hears sharp cracking sounds along the hull. At first he thinks it is ice, but the noise is too regular. Too many impacts in quick succession. The captain orders the boat to level off and then ascend slowly to periscope depth. The cracking stops as pressure decreases. The executive officer radios a terse message back to fleet headquarters. Hull integrity event. Returning to base. K-367 surfaces 200 kilometers east of Iceland at dawn. The deck officer climbs topside and immediately sees rubber debris floating in the swell. He counts 28 detached tiles drifting away from the hull, each one a meter-square patch of synthetic rubber that should be glued to steel. The tiles are buoyant, held up by thousands of internal air voids. They will float for hours, maybe days, marking the submarine's patrol route for any NATO aircraft or surface ship. The gaps in the coating create turbulent flow over the bare hull sections, generating noise. Worse, the exposed steel reflects active sonar. K-367's acoustic signature is now higher than an uncoated Victor-class boat. The stealth advantage has inverted into a liability. An anechoic tile works by converting sonar energy into heat. The rubber matrix contains thousands of microscopic air-filled voids, each roughly 2 millimeters in diameter. When an active sonar pulse strikes the tile, typically between 14 and 22 kilohertz, the acoustic wave compresses these voids. As the air inside each void compresses and expands, Friction between the rubber and air converts kinetic energy into thermal energy through a process called viscous damping. A properly designed tile absorbs 85% of the incident sonar pulse, reflecting only 15% back to the enemy receiver. That 65 decibel reduction in echo strength cuts detection range by more than half. At depth, hydrostatic pressure works against the tile. At 200 meters, seawater exerts 20 bar of pressure on the tile's outer surface. That pressure compresses the rubber matrix unevenly because the inner bonding layer is shielded by the tile itself and experiences lower stress. Meanwhile, the steel hull underneath cools as the submarine descends from 18-degree surface water into 4-degree deep water. Steel contracts as it cools. The outer rubber tile surface, compressed by seawater pressure, actually expands slightly. This creates a differential. The steel shrinks while the rubber grows. The mismatch generates shear stress at the adhesive interface, trying to peel the tile away from the hull. The numbers tell the failure story. Steel contracts by 0.12 millimeters per meter for every 10-degree drop in temperature. Rubber, under pressure compression, expands by 0.18 millimeters per meter. On a 1-meter square tile descending from 18 degrees to 4 degrees, the steel backing shrinks by nearly 0.17 millimeters, while the rubber tries to grow by 0.25 millimeters. That 0.42 millimeter mismatch across the adhesive bond creates a shear stress of 1.8 megapascals. The original epoxy adhesive, TS-NII 45 used, could withstand only 1.2 megapascals before failing. The bond was guaranteed to break every time the submarine dove below 200 meters in cold water. Once a single tile edge lifts, the failure accelerates. Seawater intrudes under the lifted edge and contacts the adhesive layer. Dissolved salt ions attack the epoxy polymer chains, a process called hydrolysis. The bond strength drops by 40% within hours. Pressure differentials pump more water under the tile with each depth change. The weakened adhesive cannot resist, and the delamination spreads from the initial edge across the entire tile. Adjacent tiles, already stressed by the same thermal and pressure cycling, begin to lift at their own edges. The cascade spreads across the whole section. By the time K367 surfaced, 28 tiles had detached in a spreading failure pattern. TSN-I 45 engineers develop a 3-layer adhesive system to solve the problem. First, a primer coat treats the steel hull with chromate to prevent corrosion and improve adhesion. Second, a flexible intermediate layer of silicone rubber absorbs the shear stress from thermal expansion mismatch, acting as a mechanical buffer. Third, an outer bonding layer of polyurethane with 3.5 megapascal strength, nearly 3 times stronger than the original epoxy, bonds the tile to the intermediate layer. As backup, mechanical rivets are added every 30 centimeters. If the adhesive fails, the rivets hold the tile in place long enough to complete the patrol. The system is heavier and more expensive, but it survives depth and temperature cycling. North Atlantic, April 1985. A NATO SOSIS array, sound surveillance system, picks up a submarine transiting the GI-UK gap. The passive sonar hydrophones record broadband noise across all frequencies. The acoustic signature is 12 decibels below the baseline for a Soviet Victor III. 12 decibels represents a 75% reduction in detection range. The watch officer flags the contact as anomalous and forwards the recording to U.S. naval intelligence. Analysts compare the signature against known Soviet submarine classes. The propeller blade rate matches a Victor, but the hull noise is far quieter. This is not a Victor III. It is something new. U.S. naval intelligence cross-references the contact with satellite reconnaissance and signals intercepts. The submarine is a new Akula-class boat, the lead unit of a class the Soviets began building in 1984. Acoustic analysis reveals the reason for the signature drop. Tiles covering the hull are now 100 millimeters thick, more than twice the thickness of Victor III coatings. The improved adhesive system has survived operational patrols without catastrophic tile loss. The Akula's anechoic coating, combined with quieter machinery, has cut the boat's radiated noise by 10 to 20 decibels, depending on speed and depth. NATO's decades-long acoustic advantage is eroding. The acoustic reduction has tactical consequences. The Mark 48 torpedo carried by U.S. attack submarines acquires targets at a maximum range of 8 kilometers using passive sonar. An Akula-class boat with its reduced signature must now be detected within 4 kilometers before a firing solution is reliable. That 4-kilometer range is inside the Akula's own weapons engagement envelope. Soviet torpedoes can reach U.S. submarines before U.S. boats have a confirmed contact. The advantage NATO submarines held throughout the Cold War, detect first, shoot first, has collapsed. Attack submarine commanders now face the possibility of mutual detection at torpedo range, where reaction time decides the outcome. The British Admiralty and U.S. Navy initiate crash programs to develop their own anechoic coatings. The U.S. Navy accelerates a classified effort called Special Hull Treatment. Contracts go out to materials labs and defense contractors. The first retrofit is scheduled for USS Batfish, a Sturgeon-class attack submarine, in 1985. New construction submarines with tiles from the keel up are planned for 1988. The British Royal Navy pursues parallel development. After dismissing Soviet tile technology as a failure in the late 1970s, Western analysts had pointed with humor at satellite photos of Victor III boats shedding tiles. NATO now races to match a capability the Soviets have operationalized. By 1989, 12 Akula-class submarines are operational, with mature anechoic tile systems. Tile loss rates have dropped to under 5% per patrol, a reliability level that fits within standard dry dock maintenance intervals. The 3-layer adhesive and mechanical rivet backup have solved the delamination problem that plagued Victor III boats a decade earlier. Soviet submarine crews no longer surface after deep dives to count missing tiles. The coating has become routine infrastructure, as unremarkable as hull paint. The 25-year investment, from degraded Nazi samples to operational stealth, has paid off. Akula-class boats now achieve near parity with U.S. Los Angeles-class submarines in acoustic signature. NATO submarine doctrine shifts in response. Passive tracking at extended range is no longer reliable against anechoic-coated boats. Attack submarine commanders adopt close-in active sonar prosecution, accepting the risk of mutual detection in exchange for confirmed target location. New lightweight torpedoes with faster acquisition algorithms and shorter time to target enter development to cope with compressed engagement timelines. Anti-submarine warfare becomes a closer, faster, and more dangerous contest. The acoustic advantage NATO enjoyed for 3 decades has been neutralized by a technology resurrected from 1940s Nazi U-boats and perfected in Soviet materials labs. By 1990, the United States, Britain, and France have adopted anechoic coatings across their submarine fleets. Tile technology becomes a standard feature on all new attack and ballistic missile submarines. The compounds and manufacturing processes are classified as dual-use export-controlled items under international traffic and arms regulations. NATO and Soviet boats now operate with comparable acoustic stealth, and the underwater Cold War becomes a contest of sensor processing, tactics, and crew skill, rather than raw acoustic advantage. The rubber coating that once fell off Soviet submarines in sheets is now universal infrastructure, a Cold War innovation that outlasted the Cold War itself. Every contemporary military submarine uses multi-layer anechoic systems. Russian tiles remain approximately 100 millimeters thick, refined descendants of the Akula-class coatings. Western submarines use proprietary polymer composites with similar acoustic performance but different manufacturing techniques. The technology that began as Nazi Germany's Alberich coating in 1940, resurrected by Soviet engineers from degraded samples in the 1960s and operationalized through 2 decades of adhesive failures, is now the baseline for underwater stealth. The rubber coat is standard. Silence is no longer an advantage. It is the minimum price of admission.